ahead and mute. And our next speaker is Ryan Phillips. So Ryan, can you share?
Yep, 1 second.
While Ryan's sharing, I'll mention Ryan is just finishing up a postdoc with me and moving on to a position in the University of Washington in Seattle. So I think he's sitting there sweating in Seattle at the moment, and talking about the effect of chloride dynamics on substantial paraticular responses to palatal and striatal inputs. Go ahead, Ryan.
Thank you. Yeah, it's really hot here in Seattle. It's supposed to be 105 today. All right, so I'm going to talk about the effects of chloride dynamics, as John said, on substantial negative paraticular responses to palatal and striatal inputs. All right, so first off, what is the SNR? So the SNR is a nucleus within the basal ganglia. We're focusing on just in the SNR first. The SNR is a collection of neurons that are tonically active, and they provide tonic inhibitory input to downstream motor centers. So if you can get some sort of pause or substantial depression in the firing rate of these SNR neurons, then you can gate motor actions such as reaching, walking, or saccade. Within the basal ganglia, there are two different pathways that regulate SNR activity. So there's the indirect pathway and the direct pathway. In the direct pathway, if you were to stimulate these D1 neurons within the striatum, they provide inhibition to the SNR. So shown here, if you stimulate, you're going to inhibit the SNR, you're going to decrease the inhibitory output to motor centers, and you facilitate motor actions. In contrast with the indirect pathway, if you stimulate the D2 neurons, then you inhibit these GPE neurons, which disinhibits the SNR, but it also disinhibits the STN, which provides an increase in excitation to the SNR. So the net effect on the SNR is disinhibition plus excitation, which will increase the inhibition of motor centers and suppress motor output. And this is what we see in experiments. So experimentally, if you optogenically stimulate the D1 neurons of the striatum, you get this increase in firing rate. And the average response within the SNR is this decrease in firing rate. And you get a corresponding increase or facilitation of movement. And then the indirect pathway, as you predict from the model up here, you stimulate the indirect pathway of the D2 neurons right here in the striatum. You get increase in firing rate in those neurons. And you actually get some excitation or disinhibition of SNR neurons. And as you predict, you see a suppression of motor movement. And so this all seems to check out at this high level population average viewpoint. But if you look a little bit closer at what's happening within the SNR neurons, you actually get a lot of neurons that are inhibited and excited, in this case with direct pathway stimulation. And with the indirect pathway, it's kind of the same story. The average effect here in the SNR is excitation, but you have some neurons that are excited and you have a lot of neurons that are inhibited. And you also have a substantial number of neurons that have no effect. All right, so then the question is, can these diverse responses be driven by chloride regulation or chloride dynamics that can result in hyperpolarized or depolarized eGABA? All right, so what I didn't quite highlight yet is that these inputs into the SNR from the D1 or the direct pathway and indirect pathway, these are GABAergic synapses. And typically you think of GABAergic synapses as being inhibitory, which usually they are, but it's also known that they can be depolarizing. And this depends on the chloride, the intracellular chloride concentration. And to get a better understanding about that, talk a little bit about the basics of GABAergic synaptic transmission. So GABA A receptors are permeable to both chloride ions and HCO3. And together, the reversal potential for these two separate ions make up the GABAergic reversal potential by the Goldman equation here. So typically the HCO3 reversal potential is -20, the chloride reversal potential is -90, and then there's a 4-to-1 ratio of chloride to HCO3 that fluxes through the channel. And so together that sets up a reversal potential of usually close to -65, which is just below the after hyperpolarization after neuron spikes. All right, so what are the factors that regulate the intracellular chloride? So it's very simple. It's the balance of how much chloride comes in and the chloride load versus how fast can the cell extrude chloride through the KCC2 pump. And then another thing that can happen is, so based on the balance of this chloride extrusion capacity and chloride influx, you're going to set the intracellular chloride concentration, which in turn will set E-GABA and determine whether or not the GABAergic reversal potential is inhibitory or excitatory, or potentially shunting. And then also, if you get a very large transient chloride load, you can actually get a biphasic response, where initially you get strong inhibition, but due to the substantial chloride influx, you actually get a hyperpolarization of the chloride reversal potential, which can actually shift the GABAergic reversal potential to become depolarizing. And that's how you can get an inhibitory to excitatory effect. All right, so when are chloride dynamics important? So the first one is if you have a large chloride load, a tonically high chloride load. So this can shift and overcome the chloride pump and shift the intracellular chloride concentration to higher levels, which can give you potentially depolarized E-GABA. And also a small compartment size. So you have a very small compartment size and you get a transiently high chloride input. On relatively short timescales, you can get short-term ionic plasticity where you get this large chloride influx and then a fairly fast increase in the intracellular chloride load, which can give the biphasic responses that we saw on the last slide. All right, so let's look back in the SNR. And what do we have in the SNR? So we have converging GABAergic inputs to the SNR. If you look a bit closer at the actual cell bodies, these two different pathways form synapses on different locations of that SNR neuron. So the indirect pathway GPE neurons, they form synapses on the soma, whereas direct pathway neurons form synapses out on the distal dendrites. So GPE neurons outnumber SNR neurons and they broadly project to the SNR, and GPE neurons fire at a high tonic firing rate. So this is going to provide a high chloride load to the soma of SNR neurons. And out in the distal dendrite, as you expect, the compartment size is very small. So within the SNR, you have the potential for both depolarized E-GABA from large tonic chloride load, and you also have the potential for short-term ionic plasticity due to the compartment size. All right, so the outline for this, I already covered the introduction. So the first question I'm going to try to ask is, can chloride dynamics explain and predict the diversity of SNR responses to indirect and direct pathway stimulation? So I'm first going to introduce the SNR model, simulate SNR responses, and then compare some experimental data. And so obviously the answer to this first question is yes. So after that, after we go through this part two, we're going to go into the last part of the talk and talk about some functional implications, such as local SNR synchrony and oscillations, and if we have time, perceptual decision-making. All right, so we have a two-compartment model for the SNR. We have the soma with the GPE inputs, and we have the dendritic compartment with the striatal inputs. And these are the simple voltage equations that govern the voltage dynamics of the two compartments, which are coupled together. And then we tune the model to meet some basic experimental benchmarks, such as baseline firing rate, the magnitude of the after hyperpolarization, and some FI curve. And of course, we have chloride dynamics governed by these two this differential equation, and then the Goldman equation for calculating the GABAergic reversal potential. All right, so predictions of the model to GPE and striatal stimulation. So to get into this, first with the thing about the chloride dynamics, and again, as we talked about before, it has to do, the GABAergic reversal potential will be set by the balance of the chloride influx and the rate of chloride extrusion. So on the x-axis here in this 2D plot, we have the tonic chloride load into the soma, and we have the extrusion capacity. So depending on where you sit in this 2D space, you're going to have different GABAergic reversal potentials. So on average, for a low extrusion capacity, you're going to tend towards more depolarized E-GABA, and as you decrease the chloride load, you're going to tend towards more hyperpolarized and more inhibitory GABAergic reversal potentials. All right, so with GPE stimulation, so this is the one that goes onto the soma, if we pick different spots within this 2D space, we can get all kinds of different responses. So up here, this point B, we have a pretty low chloride load, but strong extrusion capacity. If you stimulate these GPE synapses, we predict you can get complete inhibition. If you depolarize eGABA a bit, this point C here, where you're in a kind of a shunting regime, you can have no effect on the firing rate. I think you affect the height of the action potential a little bit. And then, as you expect, as you go to a depolarized eGABA, you get excitation. And then we have two different types of what we're calling partial inhibition. The first one is just kind of within a regime in between the no effect and complete inhibition, where in this case you just have a slowing of the firing rate. And then the second type of partial inhibition, you actually start off in the complete inhibition state, but due to chloride accumulation, you depolarize the GABA and you can recover firing a little bit. All right, so the same story with the striatal inputs. So you have the same range of eGABA, and we also get complete inhibition, no effect excitation, and two types of partial inhibition. This type of partial inhibition over here, the E2, is again an effect of a gradual chloride accumulation that lets you escape from inhibition. The other type of partial inhibition you see here, you start off just slowing the firing rate, but then you transition into complete inhibition. And this is an effect of some of the short-term synaptic dynamics that I didn't have a chance to talk about, but the striatal inputs they undergo short-term facilitation. So the synapses are actually becoming stronger during the stimulation period in this case. All right, so then the new response we see with the striatal stimulation is that you can actually get a more extreme case of this second partial inhibition, where you get really rapid accumulation of chloride. And in this case, we would predict you can get a biphasic inhibitory to excitatory response. So you start off with really strong inhibition, which transitions into excitation. All right, so let's compare this with experimental data. So the collaborators at CMU, Aaron Guinness, we collected some recordings to see, to test our model predictions. And so what we see is that we get all the different types of response types that we would predict. And surprisingly, we actually even see some biphasic response with the GPE stimulation. The ratios between of the responses are very different for these two, as you'd expect. So with GPE stimulation, we do see a couple biphasic responses, but there are very few of them. Mostly what we see is partial inhibition and some excitation, but very few neurons are actually completely inhibited. Whereas with striatal stimulation, we see a lot of neurons that are initially strongly inhibited, but we also see way more of these biphasic responses, which indicates, as you expect, that in the striatal or in the distal dendrite, where you have a small compartment size, you have more likelihood to have a fast chloride accumulation. And then we also have quite a few more excitatory responses in the GPE case, which you'd expect with the large tonic input from the GPE onto the SNR. All right, so the key points to take away from here is that eGABA and the SNR neurons are not purely inhibitory, and that eGABA can dynamically change in the order of seconds. All right, so the first answer to the first question in the talk was is yes, that chloride dynamics are important within the SNR. And so next we want to look at some of the potential implications of this. The first one is local SNR synchrony and oscillations. All right, so within the SNR, there are local collaterals, although they're very sparse. On average, an SNR neuron receives 1 to 4 inputs from a neighboring SNR neuron, but they do exist. So there's an example shown here of a connected pair in a feed-forward connection. So what we want to ask now is, can changing eGABA affect the synchrony of connected pairs within the SNR? And to do this, we're going to use phase response curves. So a phase response curve characterizes how a stimulus at a certain point in the phase can advance or delay the onset of the next spike. So in this example here, you have a stimulus that happens in the middle of the phase, so 0.15, and we have a hyperpolarized eGABA. So what this does is causes a delay. Whereas if we have a depolarized eGABA and we stimulate the same point, we'd actually get an advance. All right, so what we did is calculate or quantify the phase response curves. So these curves are characterize the advance or delay that happened as a function of the stimulus phase here. And we did this for E-GABA from -50 to -60. So you take the first case of -60, what you see is that no matter where you stimulate within the phase, you always get a delay. But this delay peaks at roughly about 0.75. And then as you depolarize E-GABA, then you start to dip into some advances. And so in the case of -50, you're almost always going to advance the next phase until you get to about 0.8, where it transitions back to a delay. All right, so we can use these phase response curves to predict the synchrony within the SNR. So we're taking this first curve here at -60. It's blue now. But if you look at where this curve crosses the x-axis, you get a fixed point. In this first case, so this is we're going to use this phase response curve to predict the phase relationship between two neurons in a unidirectional feed-forward connectivity pattern. In this case, you would expect a fixed point roughly at synchrony here, but this is unstable. So the histogram right here, which shows the timing of the input to this postsynaptic neuron, shows that you can have a pretty wide spread of the synchrony here, or the relationship. However, it does tend to stay close to synchrony. So as you move to more depolarized cases, so in this case -55, then you actually get a stable fixed point, and you get stable phase locking here, indicated by this histogram. And you move farther to -55, and the phase locking moves over to 0.8, but again, it is stable, indicated by the histogram here. All right, so if we put this all together and create a histogram from -60 to -55 for E-GABA, we can actually predict how the synchrony in this feed-forward pair would change as a function of E-GABA. So for very depolarized E-GABA, you get pretty close to synchrony, but then as you hyperpolarize E-GABA, you shift towards being antiphase or less synchronous. And then as you become more and more depolarized, you trend towards synchrony again. All of this fixed point becomes unstable, and so the histogram of the spike times spreads out. All right, so we take a little bit of a closer look at what's happening over here on the left-hand side for hyperpolarized E-GABA. When we have these unstable fixed points, is we actually get oscillations. And these oscillations show up as transient dips in the firing rate of the postsynaptic neuron. These happen at roughly 1 to 2 hertz. All right, so another way to look at these oscillations is in the input phase. And so this is the phase of when the presynaptic neuron fires relative to the phase of the postsynaptic neuron. And you can see this really nice, clear oscillation in the input phase as a function of time. And so using this, you can understand, so using this and the phase response curve, you can understand how this oscillation occurs. These are phase sloping oscillations. So in the case where we have this unstable fixed point, if you pick a point here, so we start off at 1, so you're roughly synchronous, you're close to the fixed point, but the phase response curve predicts that you get a delay when you're here. So you go up and you get a delay, and you get kicked back in the cycle a little bit, and then you get a bigger delay, and you can go through the cycle and you get bigger and bigger delays, and you shift your phase relationship until you get down here to where the phase response curve is very small, and then you start getting very small changes in the phase progression, and you get stuck relatively close to synchrony until you get kicked around the other side and the cycle repeats again. All right. So one thing that, so the shape of this phase response curve is highly dependent on the reversal potential. So if you were to increase the, or hyperpolarize the reversal potential more, the peak of the phase response curve is going to grow, and you're going to get larger and larger delays. So the effect of this is that you're going to get bigger kicks that are going to delay your progression even more, and you'll go through the cycle faster and faster. And so if you change E-GABA, this is exactly what you see. So at roughly -58, you start out with oscillations at roughly at 1 hertz. And if you hyperpolarize E-GABA, you can get up to roughly 3 hertz for these types of oscillations. All right, so these oscillations that are shown here occur in 2 identical neurons, which isn't necessarily a very realistic case. So we did check to make sure that these types of things can happen in a wide array of settings. So we changed the firing rates between the 2 neurons, increased the overall firing rate, added Gaussian noise, synaptic delay, looked at multiple presynaptic neurons and some 3-neuron motifs. And the general conclusion is that these types of oscillations are very robust to all these different perturbations. I don't have time to go into all the details of these, but happy to answer questions about them after the talk if there's time. All right, so another test of how robust this is was to see if we still get these oscillations in a larger network of the SNR. So I constructed a 100-neuron SNR network that's heterogeneous with random connectivity. So the connectivity profile is shown here with this histogram with the number of, so there's number of connections and the number of neurons with those connections. So the average number of connections or inputs to a given SNR neuron is 2. And as you change E-GABA within this network, you change the firing rate. So low E-GABA, you get a lower firing rate, increased CV, and higher E-GABA, you get an increase in firing rate. And in general, a decrease in the CV. That is the effect of the local SNR collaterals. All right, so to cut to the chase, with depolarized E-GABA, we do still see these slow oscillations. I've highlighted a couple shown here. So this 2D plot here shows the cell ID and then the power spectrum. And you see some peaks here at close to 1 hertz. And so I pulled out these 2 examples here. So cell 46 and 18, and we get these nice peaks in the power spectrum. And if you look at the frequencies, sorry about that. So yeah, if you look at the frequency for these different neurons, you get these nice oscillations in the frequency. One surprise is that for very depolarized or excited for E-GABA, we actually start to see in the larger network slow oscillations that occur too, which was a bit of a surprise. All right, so the key points from this part on SNR synchrony and oscillations is, so far what we have is that the chloride load to the SNR can change E-GABA, which in turn can change or regulate the SNR synchrony and the emergence of these slow oscillations. All right, so are there implications or and some experimental comparisons we can make? So yes. So in dopamine depletion, the classic response is that the firing rate of the GPE neurons actually decreases. And from our model, you would predict that if you decrease the firing of the GPE, you're going to decrease the chloride load to the SNR neurons, and you should hyperpolarize the E-GABA. So you get a shift in the chloride load, which will shift E-GABA and shift you from potentially asynchronous state to synchronous state with some oscillations. And this is exactly what we see in the experiments. So in dopamine depletion, you see an increase in the synchronous pairs within the SNR, and you see the emergence of these slow oscillations. The next question is, can you counteract these? So can you optogenically stimulate the GPE to increase the tonic load back to the SNR, which you would predict from our model, you should shift this back up in the chloride load and increase E-GABA, and that should shift you on this curve, so you should decrease synchrony and remove the oscillations. So we did that experiment. So we identified some of the slow oscillatory units within the SNR, shown here, identified by the power spectrum. And then we optogenically stimulated GPE neurons. And one surprising thing is that you actually get no change in the firing rate of SNR neurons, but you get a substantial reduction in the oscillations of these neurons. All right, so key points to summarize this. So the main idea is that the GPE to SNR projections provide a tonic chloride load that tunes SNR E-GABA, and through local collaterals within the SNR, this E-GABA can regulate the local synchrony and the emergence of these slow oscillations. All right, so finally the last thing is decision making and dendritic chloride regulation. All right, so a paradigm for decision making is a perceptual decision making task, where an animal looks at a screen with dots that are moving different directions, and their task is to decide which way on average these dots are moving. And within the SNR, what you see from experiments is that, this is a model here, but you see a ramp in activity in the direct pathway for neurons that are trying to gate a left versus right decision. And once you accumulate enough evidence in this ramp in the striatal input, then eventually what you get is a nonlinear and abrupt pause in the SNR activity that can gate a saccade to look left or right. And so with our idea here that the GP input to the SNR can tune E-GABA, we would expect the same thing with a dendrite. So this first panel right here, and see if you, or I guess back up a little bit, we brought back the SNR network, which has a mean firing rate of roughly 25 hertz. And then the first thing we did is we changed the tonic input to the soma and looked at whether or not we can influence the dendritic E-GABA. And yes, you can. So as you increase the chloride load in the soma, you depolarize the somatic and the dendritic reversal potential for GABA. So next, what we did is we constructed a ramp in the firing rate of the striatal synapses for these neurons, and then we characterized how the chloride load affects how long it takes for the SNR activity to decrease below some sort of threshold to generate a pause. And what we found is that as you increase the tonic chloride load, as you expect, you're going to weaken striatal synapses on the SNR, and it's going to take longer for you to pause in this type of paradigm. All right, so then to conclude, again, so the GPE to SNR synapses provide tonic chloride load to the SNR neurons. The tonic chloride load tunes somatic and dendritic E-GABA. And then E-GABA can regulate the local SNR synchrony, emergence of the slow oscillations. And finally, E-GABA can also tune the response times within the SNR with it for decision-making tasks. All right, and I'd like to thank John Rubin, my advisor at Pitt, and then also collaborators at Carnegie Mellon, Aaron Giddis, Ian, and Tim. All right, I'll stop there.
Thanks, Ryan.
Yep.
So we have a short amount of time for questions. Again, questions can go in the chat. Hands can be raised, or as a backup, you can just unmute. So does anyone have a question for Ryan? Just gonna give a minute. People can gather their thoughts. And if not, we'll move on to the next talk. Going once.
Yeah, I'll ask a question.
Okay. Bill Meyer, go ahead.
Yeah, so your talk is mainly focused on chlorides, and I like it. So great talk, thanks for that. But I was wondering about the bicarbonate. That seems to play less of a role in your talk, but the reversal potential, the formula you give for it, depends on it. So what's the motivation? Because if this bicarbonate quantity is large, then chloride hardly has an influence.
Right. So yes, if you could shift the bicarb, then yes, you could affect the GABAergic reversal potential as well. In the intracellular space, the bicarbonate concentration is regulated by a really fast, I think, catalytic reaction. And so in general, it's really hard to change the intracellular bicarb. I think there might be some diseases or some cases where you can affect the extracellular bicarbonate, but that's not really in the context of dopamine depletion or healthy animals, I don't believe. So in general, you can assume the bicarb to be fixed.
Okay, thanks. So actually, we're down to sort of the last minute here. So Ryan, why don't you go ahead and stop sharing?